Problem 21. Notice that 6 subtract 2 equals 4, 9 subtract 5 also equals 4, and 11 subtract 7 also equals 4. That means if we find the common multiple of 6, 9, and 11, and subtract that by 4, then it will satisfy this problem. So first, let's find out the least common multiple of 6, 9, 11. That is 2 multiply 3 squared multiply 11 equals 198. And how many? 198 subtract 4 is the number we are looking for, and it's the smallest one. So how many of these numbers are 3-digit integers? We can use 999 to divide 198, and that equals 5 with remainder 9. That means there are 5 numbers that are 3-digit number, and they are the common multiple of 6, 9, and 11, and we subtract each of them by 4, then that's the number that satisfies the problem. So these numbers will be a total of 5. Problem 22. Let's assume the length of the square is L, and because E is the midpoint of DC, therefore EC equals L over 2. And because these two angles are the same and EC is parallel to AB, therefore, if we draw a line from F that's vertical to EC and assume this is H1, and also a line from F that's perpendicular to AB, that's triangle ABF's height, and we assume that's H2. So H1 divide H2 equals to EC over AB equals 1/2. Because H1 plus H2 equals L, so we can solve these two equations and we get H1 equals 1/3 of L. Now if we add the area of ADEF and the area of triangle ECF, it equals half the area of the rectangle, that's 1/2 L squared. And that means ADEF is 45 plus ECF is the area is 1/2 multiply EC is L over 2, and the height H1 is L over 3. It equals 1/2 L squared. And that means 5 over 12 L squared equals 45, and L squared equals 108. Problem 23. If we choose any of the 3 vertices out of the 8, we will get 8 choose 3 total combinations, and that's 8 factorial divide 5 factorial divide 3 factorial. That equals 8 multiply 7 multiply 6 divide 3 multiply 2. That's 56 total choices. And then if there are at least one side of the triangle is also a side of the octagon, then that means if we choose two neighboring points, that means it's the same as we choose this line. And how many choices are there? There are 8 sides, so that means 8 choices. And then we choose the third vertex of the triangle from any of the 6 points that are left. So that's 6 total choices. And in there is one case that's double counted. That's the 3 neighboring vertices. So how many of these combinations are there? There are 8. So we subtract that. And that means there are 40 of these triangles. And 40 over 56 equals 5 over 7. Problem 24. For simplicity, we can assume the size of the cube is 1. And because J and I are midpoints of FB and HD, therefore the length of JI equals to the length of BD. And it equals to square root of BC square plus CD square. That equals to square root of 2. And then let's calculate the length of EC. The length of EC equals the square root of EA square plus AC square. Let's connect AC here because AC is perpendicular to EA. So AC also equals BD. That means this equals 1 plus 2 equals square root of 3. And then the area of EJCI equals 1/2 of JI multiply, because EC is perpendicular to JI here. So the area of EJCI equals double the area of the triangle EJI. And that means it equals 1/2 JI multiply EC. And that's square root of 6 over 2. And that R is the ratio of the area of the cross-section EJCI to the area of one of the faces of the cube. So one of the faces of the cube, the area is 1. So the ratio R equals square root of 6 over 2. And R squared then equals 6 over 4. It equals 3 over 2. Problem 25. Because 2 to the power of 8 equals 256, it plus 1 equals 257, and the smallest cube larger than that is 7 to the power of 3. It equals 343. And for 2 to the power of 18, it can be written as 2 to the power of 6 to the power of 3 plus 1. And 2 to the power of 6 equals 64 to the power of 3 plus 1. So how many cubes are there? It means we use 64 subtract 7 plus 1 because 7 is also in between. So that means there are 58 cubes.